Great. Thank you so much to Jamie and Martin for inviting me to be a part of this. It's always a great pleasure and great fun to talk to BHI folks. And without further ado, let me share the slides. So, yep, okay, that's fine now. So I want to talk about the distinction between physically reasonable and physically unreasonable spacetime in the context of the search for V or A, as you wish, theory of quantum gravity. A will be more appropriate given the sort of examples I will be discussing. This is the plan. I hope to be speaking for about 30, 40 minutes or so. And I will sort of give you the whole surprise in section 1, and then sort of fill in the holes when it comes to motivation and one particular way of thinking about interpretation of a physical theory, and then 2 case studies. That is ADS-CFT and black to white hole transitions. And those case studies, obviously, I will be using to sort of motivate my general claim. So let me begin with a general claim. So in this paper from '98, Gordon Bellot argued that our interpretative beliefs about electromagnetism are open to revision in light of quantum effects. And what he means by that is the Aharonov-Bohm effect. Actually, why not have a look at this? Why don't we have a look at this quote in a bit more detail? So Gordon says that attention to quantum mechanics can shift the balance of power among competing interpretations of electromagnetism. There is an ambiguity inherent in the construction of a quantum model of a charged particle moving in an electromagnetic field, and distinct interpretations of electromagnetism suggest different ways of resolving this ambiguity. And the empirical success of one or another quantum treatment can then have repercussions for attempts to interpret electromagnetism. And in particular, Gordon argues that in the aftermath of the Aharonov-Bohm effect, one is forced to accept that electromagnetism is either indeterministic or non-local. And so what we have here is a case where we have a classical theory, the classical electromagnetism, and we have a sort of quantum successor or a more fundamental theory, if you wish, of that classical theory. Sort of some features inherent to the quantum treatment of the theory started with sort of feed back to our interpretation of what happens at the classical level. I will argue, basically, that if we tentatively accept some of the proposals that people seem to seriously consider in the context of quantum gravity, we are in a partly similar situation when it comes to general relativity, which is sort of analog of the electromagnetism, of the classical electromagnetism, and quantum gravity, which is successor, which is the supposed successor of the classical theory and an analog of the quantum theory, with some differences, because the Aharonov-Bohm effect is, of course, a well-tested, actual effect. In context of quantum gravity, we are dealing with various more mathematical or more phenomenological models. But I will come to that. But the basic upshot is that I think when it comes to relation between classical GR and some approaches to quantum gravity, we find ourselves in a case where some features of those attempts at constructing a theory of quantum gravity seem to be forcing us to go back to the classical theory and revise some interpretative beliefs we may have about classical GR. So that's the claim I want to be arguing for. And yeah, of course, I think that's sort of the best way of making sense of some things that happen in quantum gravity. Let me now flesh this in a bit more detail. So here's what I think is a sort of natural, or at least natural to a philosopher of physics attitude to classical GR. So we have all sorts of space-time models, all sorts of, um, Lorentzian form manifolds or Lorentzian n manifolds, um, and the distinction concerns which of those are physically reasonable and which of them are merely mathematical constructions. And so proposing such a distinction amounts to asserting that not all models of the theory equally well represent physically possible situations. It's merely a subset of the models that represents some physically possible situations. Now, I will just restate the claim I made on an earlier slide. We have a sort of commonly accepted in the theoretical physics community view that GR breaks down at high energies. And of course, we have very little, if any, experimental evidence to serve as a guidance in construction of the theory of quantum gravity. So I think it's natural that physicists turn to model with promising mathematical features and sort of irrespectively of their status in the classical theory. And so again, you could ask whether a physically unreasonable from the point of view of sort of some interpretative ideas about classical GR could be useful in search for quantum gravity. And I think the answer is not only yes, it could, but it actually is, and the use of such models can be substantial. So they're not merely type models, but what some people propose is seeing them as approximately true descriptions of some subsystems or physical processes in the universe. And so I think we find ourselves in quite a, philosophically speaking, interesting situations because perhaps our views on what's a physically reasonable relativistic spacetime should be sort of open to revision and reinterpretation in the light of attempts at construction of the successor of the theory. But because all of this happens in a non-empirical way, because we have very little empirical data, if any, this could be a sort of potentially promising case where something like philosophical insight or conceptual analysis and things like that could be useful. So now let me say something more about interpretation of a physical theory. Consider this could be stated in different ways, but let me state one I find to be sort of the easiest to think about. We have a set of models of a given physical theories, and GR, that's just the Lorentzian manifolds. And without additional restrictions, it is easy to find examples of various features we may see as problematic. So, limitations of predictions or various forms of indeterminism or space invaders type scenario or hypercomputation and other features that we do not seem to be seeing so much in our immediate environment. But finding these examples of instances of those features may be much harder if we just restrict the set of models to a somewhat smaller set of physically reasonable ones. And I think this sort of attitude is yeah, it's of course very old. I really like the example where in 1951, Einstein asks whether spacetime such as Gödel spacetime containing closed time-like curves are not to be excluded on physical grounds. And I will say a bit more about what those physical grounds could be in a few more slides. But before I get there, let me make one provisor. So I think people use very different words. Sometimes we speak about simply a physical spacetime or physically reasonable, as uh, yeah, people such as J.B. Manchak, and other people say physically salient or physically cogent or physically significant. And sometimes, like in some of Fletcher's work, a distinction is made between more metaphysical notion of physical reasonableness, um, which has to do with the question which spacetimes represent genuine physical possibilities, and more epistemic notion of physical significance, what users of the theory can assert about different domains described by GR. I hope to remain neutral on whether the sort of conditions for being a physically reasonable, salient, cogent, significant, whatever space-time should be read in more metaphysical way or epistemic way or some entirely different way. I hope not much will hinge on it in this talk. So I want to remain neutral on how those conditions should be interpreted. I think it's sort of enough that in both physical and sort of foundations of physics practice, we seem to be positing such conditions and using them. And so here are some cases where sort of different conditions for being physically reasonable seem to have played a role. The first is acceptance of singularities after Penrose's and Hawking's singularity theorem. Those theorems show that singularities are not merely features of highly idealized symmetric models, such as Schwarzschild spacetime or perfectly spherical gravitational collapse, but are unavoidable under rather generic conditions. And so then, before this sort of singularity theorems, you could try to say, oh, maybe the singularities are just sort of artifacts of those highly symmetric idealizations and approximations. It's much harder to do so after Penrose and Hawking theorems, because those theorems in their premises capture a very wide general class of spacetimes. And so one could say that sort of if my notion of physically reasonable spacetime is that it satisfies some causal condition and some energy condition, and yeah, it has a trapped surface, for instance, then no matter whether it's spherically symmetric, it has a spherically symmetric source or not, it will develop a singularity. There's another example of something like this is a sort of long back and forth in the foundations of physics literature. I'm citing here Manchak, but I could just as well cite people like Ehrman and Norton and Hogarth and Andreka and Nemeti and a bunch of their collaborators. So that's the question of whether we could find some physically realistic, in some sense, example of Malam and Hogarth spacetimes. And of course, it would be interesting if we find them, because we could perhaps algorithmically decide some things that we cannot do in finite time, because we might have some resources to kind of implement relativistic hypercomputation. And so in this exchange that sort of begins in the early 90s, all sorts of problematic features of known Malam and Hogarth spacetimes were raised. For instance, infinite blue shift or violations of certain energy conditions, and so on. And in response, new examples of Malam and Hogarth spacetimes satisfying the properties that previously known model Malament-Hogger spacetimes violated were constructed. And I think, a recent paper by J.B. Manchek is sort of most up-to-date example of a Malament-Hogger spacetime satisfying numerous conditions that previous examples did not. And so what happens here is sort of we have a Malament-Hogger spacetime and say, oh, it's not physically reasonable because it violates this or that property. And then people like Manchek come and say, oh, no, but look, I can come up with a Malament-Hogger spacetime satisfying these properties and a bunch of others on top of that. And so in cases like this, what I suggest a philosophically interesting and useful way of looking at them is from the perspective of what is a physically reasonable spacetime. Now, naturally, it would be great, but life is not so nice and simple. And I think we cannot expect that there is a unique condition for being physically reasonable, applicable to all contexts. It would be great, but it's just not going to happen. For instance, in cosmology, people often take something like homogeneity with some degree of anisotropy plus causality condition to be features of physically reasonable models, but in some other contexts, such as the question of, oh, what are the possible distributions of matter allowed by GR? Of course, this would be much too strong. And if we're dealing with isolated systems, that would also be inappropriate because we model those with the help of something like asymptotically flat boundary conditions. And so I think it's important to, when thinking about conditions for being physically reasonable spacetime, to bring in this quote from John Ehrman, who points out that the literature on cosmic censorship can be confusing to the casual reader because it mixes together a number of different senses in which a model can be physically unreasonable. Among them, it may be literally physically impossible, involves unrealistic idealizations, and there's no reason to expect that more realistic counterparts will also have some features such as naked singularities, or the model is physically possible but involves such rare features as to leave no reason to think that anything like the model will be actually encountered. Of course, that's a quote from 95, but I think a good case could be made that literature on cosmic censorship remained confusing with respect to many of those aspects. There seems to be no one-size-fits-all condition or a set of conditions, and so conditions for kind of distinguishing physically reasonable spacetimes from physically unreasonable spacetimes are at best contextual, because there's no single condition appropriate for all circumstances, and can be interpreted in different ways. For instance, may capture the sense in which spacetime is useful as a model for some particular class of physical phenomena, the solar system, observable universe, binary black hole systems, or the condition may represent a restriction on possible ways in which spacetime as a whole could be. And the sort of considerations in global structure of spacetime that philosophers of physics paid some attention to would fall, for example, into this category. For instance, conditions such as maximality conditions in the form of inextendability or auto-hole freeness conditions could be interpreted as a restriction of this sort. And of course, there are multiple ways of drawing the distinction. So we could use local properties, such as being a solution to the Einstein's field equations with a particular source term, or being a spacetime satisfying some energy condition, or we could use global properties, including either global symmetries or causal properties or other global or spacetime properties. We could use various parameters, for instance, value of the cosmological constant, and we could use something for that, for the lack of better expression, but I don't really like this one, but anyway, let me call it relational features, such as stability under some kinds of perturbations. And so that's another way of sort of spelling out the distinction between reasonable spacetimes or features of spacetimes and unreasonable ones. For instance, one could say, we should not expect, I don't know, Cauchy horizons within the curved black holes to show up in our universe, and hence should not expect Mallam and Hogarth space features to rise in our universe and time machines to rise in our universe, because the Cauchy horizons in rotating black holes, if cosmic censorship, if some forms of cosmic censorship are true, are unstable against some kind of perturbations, and so they will not, arise in generic cases, and so we should not think that Cauchy horizons and all those associated nice things are physically reasonable features of the subsystems within our universe. Good. Let me try to wrap this up. I sort of tried to convince you that at least one natural attitude towards interpretation of GR is that the business of interpretation is about drawing a distinction between models which represent ways our universe could be in the effective domain in which GR applies, and models which do not represent ways our universe could be, and hence, in short, with the distinction between physically reasonable and unreasonable spacetimes. I think there could be other sort of interpretational attitudes to GR, but I think this is at least a very natural one, and I think this sort of captures a lot of the work, or could possibly capture a lot of the work in the foundations of GR that has been done. Okay, maybe that's a good moment if anyone would like to strongly object to something I have said so far or ask a clarificatory question. Well, if not, then it's great. And let me continue to my two case studies. So what's going to be happening now is we have those two case studies, ADS CFT and black to white hole quantum transitions. And I will first sort of describe the spacetime model used in, very briefly, of course, used in those constructions, and then spell out few ways in which, from the perspective of the classical GR, it may be this model, ADS spacetime or white hole spacetime, can be thought of, or may be thought of, as unreasonable. So I think we're all familiar with ADS spacetime. Here's one particular representation of a four-dimensional anti-de Sitter spacetime. And it's also useful to have a notion of asymptotically ADS spacetime. And that, loosely speaking, is the idea that we have a submanifold with boundary where the metric has deviations from the anti-de Sitter metric, but smoothly goes to ADS outside of that submanifold. The anti-de Sitter spacetime is extremely useful because of the ADS-CFT duality, which is sometimes described, and I hope you'll excuse the sort of level of generality I have here, as a physical equivalence between the gravitational theory, that's anti-de Sitter spacetime, asymptotically anti-de Sitter spacetime with compactified additional dimensions, and a conformal quantum field theory defined on the boundary of that spacetime. And what's essential for the ADS-EFT duality was the observation that the dimensional ADS spacetimes have the same symmetry group as some conformal field theories in the -1 dimensions. And that in turn allowed for the construction of appropriate limit relations between the bulk and the boundary, and that allowed for sort of construction of the matching observables in those two theories. Um, okay, so this is great. And of course, the ADS-CFT duality became a sort of field of theoretical physics on its own with applications to strongly coupled systems, Clark-Gluon plasma, information loss problem, and led to construction of other holographic dualities, not necessarily based on the anti-de Sitter-like spacetime on one end. And so in that sense, ADS-CFT duality seems to be a sort of, at least when you hunt it by papers and textbook published, a very fruitful idea. But of course, I sort of foreshadowed this by talking about Malam and Hogarth spacetimes. I think if you come from a philosophy perspective, foundations of physics perspective, you may be a bit worried about ADS-CFT. Why? Well, first of all, ADS has a negative cosmological constant, and that implies that the spacetime is not globally hyperbolic. So for any point P, the past light cone of P sort of rapidly widens, and for any such point, there will be a causal curve with infinite proper time, which is fully contained in the past light cone of that point. This, which leads to a sort of space invaders-like indeterminism in which the information can always sort of arrive from the asymptotic boundary that we have in the spacetime, and so to speak, influence the events in the bulk. And so unless we have some additional boundary conditions which sort of dictate us what happens at a time like infinity, the initial value problem is not well posed. And of course, the boundary conditions are non-unique because we could pick all sorts of boundary conditions. For instance, the light arriving at the time like infinity could get reflected, or it could get swallowed, or all sorts of other things it could happen to it. And of course, note also that the lambda CDM model has, well, positive sign of the cosmological constant. And so in this sense, the ADS, asymptotically ADS spacetimes have no chance at being approximately correct cosmological model for a wild class of simple dark energy models. In particular, not for any dark energy model that posits simply a cosmological constant. Now, ADS is also quite a fun spacetime because it can be interpreted as a vacuum spacetime with cosmological constant, but also a spacetime with a weird perfect fluid source. And if we interpret it as a spacetime with that fluid source, then the weak energy condition is violated. And so, of course, any stronger energy condition will also be violated. And so sort of if your preferred way of making the distinction between physically reasonable and unreasonable spacetime is via local properties such as energy conditions, then and if those would include the weak energy condition or any stronger energy condition, in the sense of any energy condition that implies the weak energy condition, that wouldn't be very well for ADS. And finally, numerical simulations suggest that D plus 1 for D equals 3 or more, ADS spacetimes are unstable. So arbitrarily small perturbations lead to gravitational collapse. So what does this mean for us? Well, this means that if my favorite condition for a spacetime to be physically reasonable is the sign of cosmological constant, weak energy condition, or any other which applies that, global hyperbolicity or I guess Penrose's version of strong cosmic censorship, which, well, have a look at Klaas's Landsman recent paper, but Penrose is one of Penrose's versions of strong cosmic censorship says that only global hyperbolic spacetimes are physically reasonable, or nonlinear stability under particular boundary conditions used in those calculations, then the ADS lands on the wrong side of the reasonable unreasonable divide. And so then acceptance of ADS CFT framework seems to force me to at least argue that these conditions are not necessary for the spacetime to be physically reasonable, no matter how natural they may seem in the context of classical GR. Sort of usefulness of the ADS CFT correspondence kind of triumphs over those constraints. At least from, I think this is something that a person accepting that ADS CFT is sort of on the right track on the road to quantum gravity or something like that should say. And most of those points will carry over to asymptotically ADS spacetimes. At least some of those will carry over to asymptotically ADS spacetimes. Okay, let me now go briefly to a second example that I have. So that's the black to white hole quantum transition. Yeah, it's BHI, so I'll just very briefly remind us what the white part of that business is. Of course, GR is invariant under time reversal in the sense that if we take time orientable spacetime with chosen temporal orientation and change all of the past pointing vectors to be future pointing and vice versa, we also get a spacetime. And so the change of temporal orientation results in a typically non-equivalent another model of the theory. And so if we do that to a black hole spacetime, we have a white hole spacetime. And in that spacetime, loosely speaking, instead of gravitational collapse of ordinary matter imploding to form a massive object with horizon, which kind of pulls in matter and contains future singularity, white hole spacetime is also a massive object with horizon, but horizon acts repulsively. It's a one-way membrane, but you can sort of only exit out of the white hole, you cannot enter in, and the singularity is in the past, and at some point the horizon will disappear by transitioning to ordinary matter. Now, the black to white hole quantum tunneling idea is the idea that in the late stages of semi-classical black hole evaporation, we'll get some additional strong field non-perturbative quantum gravitational effects, partly located outside the horizon, which will lead to a repulsive bounce. And the bounce phase will be represented by gluing the time reverse of the black hole metric, that is the white hole solution. And so this is sort of like the bouncing cosmologies that many people have considered, but apply to a black hole context. I think the first such model is by Hajicek and Kiefer from 2001, but kind of with the work of Haggard and Brovelli and Vidot and their collaborators, there was a large proliferation of such models, mostly done in the context of the loop quantum gravity. Here's a partial, not super up-to-date list of the work done on those models. It's important to note that because most of this work is done in the loop quantum gravitational context, most of those authors will consider smooth GR geometry to be something like effective, merely effective description of the fundamentally more discrete end quantum structure. So the sort of nice and smooth structure of relativistic spacetime we love, that we like and love, is seen as just an approximation for them. So sort of schematically, what happens is that one wants to sort of replace this diagram of a complete black hole evaporation with one like this, and the regions A or B are where the sort of quantum gravitational strong field effects happen, allowing one to sort of glue this and this classical solutions together. And one obviously immediately we can see that this one doesn't have some of the bad causal features that the model on the left has. Okay, so well, those are the black to white hole transitions, but in classical GR, I think the situation is a bit different. We're not super excited about white holes in classical GR. I think actually there's a consensus that despite time reversal invariance of the Einstein's field equations, white holes are unphysical. Why? Well, because no physical phenomena resembling white holes have ever been observed. The only possible sort of exception to this are very, very early quasar models that have been kind of dismissed by early 70s. Second, many people have the view that the white holes are incompatible with the generalized second law of thermodynamics. But there is a controversy. I think Klaus Kiefer raises some good points in his book about this. Check out if you're interested. And I'm not particularly fond of this argument, but one could think that the white holes violate the cosmic censorship hypothesis. And there are sort of two aspects to this. The first is how to determine what comes out of the white hole if we have no epistemic access to the interior. And the second is sort of at which point the white hole decides to transition to ordinary matter. And whether we could determine that, and if so, on what basis. Okay, so now I think analogously to the ADS case in GR, we have sort of when it comes to white holes, we see that they lack some features. They're not useful as models of observable phenomena. Have this indeterministic or at least unpredictable aspect. And I think this is for most people acceptable to dismiss white hole spacetimes as physical altogether. And again, this assessment of white hole spacetimes as unphysical should change with the acceptance of black to white hole quantum transitions, because white hole spacetimes are suddenly treated as physically reasonable because they represent physics of certain subsystems, namely post-quantum tunneling stages of black hole evaporation. And moreover, some of the features that we had, for instance, the past singularity in the white hole spacetimes are sort of interpreted away because the white hole region is glued to the future of this non-singular region R used in those calculations. And so not only the status of such spacetime shifts with the acceptance of black to white hole quantum tunneling, but so does sort of relative importance of various physical features of those spacetimes. Somewhat analogously to the careful interpretation that Denis Lemke pointed out in the context of Einstein's work on the problem of motion. Okay, I'm near the end. So I gave you two examples where I think acceptance of a hypothetical quantum gravitational scenario seems to force us to revise interpretational assumptions and assessments concerning certain spacetimes in such a way that spacetimes thought to be physically unreasonable in GR are treated as physically reasonable in the new theoretical context. And I think I could have plausibly given you something like ER equals EPR as another example, but I personally find that example very hard to understand. So let me stick to these two. Um, I will just be repeating myself at this stage, but there will be something new at the end. So, well, assuming the standard cosmological model until we had the ADS-CFT, although those sort of the lambda part shows up sort of simultaneously with the ADS-CFT duality, so maybe that's not the best wording. But the asymptotically ADS spacetimes were not considered to be serious candidates for description of either the universe as a whole or subsystems within, and until the development of black to white hole quantum tunneling, white holes were dismissed as descriptions of physical subsystems within our universe. And so candidates for a UV completion of GR, i.e. a theory of quantum gravity, can and do force someone, in particular someone like perhaps me, to redraw the distinction between physically reasonable and physically unreasonable spacetimes, in the sense that the spacetimes that used in ADS-CFT or black to white hole quantum tunneling seem to be physically reasonable after all, perhaps in new regimes, but nevertheless, they sort of raise their head. And as much as I would be tempted to consider them to be long and gone and physically relevant, these sort of attempts at a future theory may and seem to resurrect some of those spacetimes, bring them from the grave, and say, look, those spacetimes you thought are physically relevant, they actually do represent or are useful in calculation of in calculating the behavior of certain subsystems. Let me go through this very quickly. One could say that those are just toy models, but I think this is not the right way to say. This is not the right thing to say because those models are, in some cases, large theoretical frameworks like ADS-CFT duality. There's significant body of literature. There's connections to some observations. And so these do not seem to be merely time models. And the second important thing is that, of course, this redrawing of the distinction between physically reasonable and unreasonable can, or some, I think at least can, and in the black to white hole transition case is associated with reinterpretation of a solution. Some features, the past singularity, are interpreted away. And perhaps something similar may happen to classical indeterminism in the ADS-CFT duality, but it would be interesting to see more explicit discussion of why the particular CFT that I have would impose unique boundary conditions on the gravitational side of the duality. So I think the methodological moral is that, as natural as it may seem, we should perhaps not get very attached to our favorite subset of spacetimes being physically reasonable. If any of those two approaches that discuss this even remotely on the right track, future physics can make good use of solutions dismissed as physically unreasonable from the perspective of classical GR. And this is the last, these are the last two things I would like to say on this. The first is, you could ask, well, can we use those unpleasant features to somehow constrain these quantum gravitational proposals? And I think that could happen. Be happy to talk about this during the Q&A. But the perhaps more interesting thing is that, in contrast with the Aharonov-Bohm case, in which Bellot made what I consider to be sort of analogous claim, the revision that happens in the cases I discussed is non-empirical. It's very theoretical features and sort of mathematically advantageous aspects of ADS, asymptotically ADS spacetimes or white holes that lead to acceptance of those frameworks, but empirical observations are not among them. The change in interpretation, that is the assessment of what counts as physically reasonable spacetime, is not motivated by a subsequent well-tested theory. And I think it's at least the right question to ask whether this kind of revision of our interpretative beliefs is more troubling than other cases of revisions. But I won't be attempting to answer this question today. Thank you very much for your attention. That's it. Just some biblio.
All right, well, thank you very much, Juliusz, for a lovely talk. So let's start having questions. So there's lots of hands up. I'm going to look at the participants list, and that should tell me who was first. So the order goes Brian, Eric, Jeremy. So Brian, start us off.
Wonderful, thank you, Juliusz. I just had a brief comment on the white hole case. I thought it looks in a way quite different from the ADS CFT case as an example of an unphysical thing, and that it's not clear, or at least it seems particularly interesting in this case, to ask whether it's the sort of unphysicalness that arises out of stability issues associated with, like we would say, thermal fluctuations are, well, are they unphysical? I mean, they're certainly rare. And so I wonder if a white hole ought to be perhaps viewed as something more associated with a stability problem rather than a physical reasonableness problem. And regarding ADS CFT, I just thought that's such an interesting example, partly because one might wish to view the space-time as being physical for the purposes of analyzing a CFT and explain, people propose explanations of confinement and any number of other things. So it's sometimes not for the purpose of analyzing space-time, but for the purpose of analyzing something else. And I wonder if you could comment on that. Thank you.
Right. Thank you. Let me comment on the second thing first. Right, the ADS CFT case may be perhaps a case where, in many cases, what we really want to say is we have this really hard to calculate problem in quantum field theory, and it just so happens that we have this almost magical duality that allows us to calculate these things more easily by going to the dual theory, calculating things, and then going back. And so in that case, I guess one would have a sort of, one wouldn't say, oh, this represents anything on the space-time side. Perhaps for the problem at hand, there is no, that doesn't even rise, right? And in that cases, one would be one have like a almost fictionalist attitude about the gravitational side. It's not really there. It's rather a convenient mathematical trick to use it as a description of this particular system. And in that case, I would say, of course, one is free to use whatever calculational methods one may wish. And there's no, I don't think there are any particular problems arising there. But I think they would if, for instance, we want to say that I think some people wanted to say, well, or for instance, solve certain bets about the information loss problem based on arguments following from the ADS CFT duality. And in that case, it seems that one should interpret the ADS side as actually representing the gravitational side of things. And if this is what one wants to do with ADS CFT or holography, then I would say the revision is sort of more substantial than in case of something like Clark using ADS CFT in calculating Clark gluon plasma. Yeah. Well, as for the first point about the white holes, so I sort of, I hope that I could sort of avoid this question because I phrased the conditions for being physically reasonable in such a way that they also included things such as stability under perturbations. So I sort of included them in how one may want to make to kind of draw the divide. But maybe that doesn't entirely answer your question.
We don't have to dwell on it. There's lots of other questions.
All right.
Yeah.
Eric, you have you're next in line.
Thanks, Juliusz. That was really stimulating. So I have a question about how how it is that you think we ought to or can understand these physical reasonability conditions or judgments of physical reasonability and the way that they have an impact on our understanding of the conceptual structure of the theory. How we're supposed to understand that with regard to our understanding of general relativity as a theory. So is it the case that when, say, someone interested in foundational work is investigating the conceptual structure of general relativity, whatever exactly that might mean, but we all claim to do that from time to time, but I'm not sure we actually know exactly what we're doing. Put that aside.
Yeah.
So is it the case that is the way you see it that there's kind of a fixed bundle, and there's the theory of general relativity, whatever exactly that may be. I'm not going to prejudice the question either way. But at least part of it are these space-time models, and part of it includes ways to think about how these space-time models may or may not bear on our understanding of GR as a physical theory. Now, are these examples supposed to show that when we approach GR, we should possibly change our understanding of how these bear on our understanding of GR as a physical theory? Or is it rather that these models show us that, in fact, we should be changing what we think of as the theory itself? That now we see that we not only need to worry about solutions to the Einstein field equations implicator, we also need to do things like throw in the machinery of ADS CFT. And we need to throw in the machinery of at least some of these perturbative canonical gravity calculations that that are involved in the white hole black hole evaporation case. I mean, white hole black hole tunneling case. And that so do you see it as changing the way that we think about spacetimes in the theory, or pushing us towards changing kind of what we think we ought to include in the theory in the first place, because these now seem like spacetimes that model phenomena that are kind of continuous in some relevant sense to the stuff we think about using classical GR non-problematically?
Wow, that's a tough one. I'm not sure what to think about the holography duality cases so much here. The black to white hole transition is sort of easier for me to grasp. So let me begin with that one. So I think in that case, it's more clearly, well, that to me seems to be like your first option. So we we had those solutions, we dismissed them as irrelevant, and then we come up with a more fundamental theory. And if we trust this theory, then in certain cases that our classical theory so far hasn't covered, we will get the phenomena which look like white holes. And so what we really are revising is rather the set of solutions that had it's more like we had those solutions already, and we thought that they were devoid of representational capacities when it comes to, in the sense that there were no subsystems in the actual universe that are represented or could be represented as white holes. But then now it turns out that they actually, after all, can be represented as white holes. And so what seems, and of course there's this additional machinery with, the additional effects that the theory does not account for, and the transition metrics that allow me to glue the black hole to white hole, and so on. But because all of those things are sort of like about domains that classical GR does not describe, at least according to people who posit black to white hole transitions, I don't seem to be revising the theory itself. The theory was about Lorentzian 4n manifolds, and it is about Lorentzian 4n manifolds. It's just a matter of which of those can represent some systems in some cases. And what happens here is rather we say, oh, here's a new set of cases where those solutions that did not represent previously now can represent. And so in that sense, I think there is not much that changes with the theory itself, if I understood your question correctly. Does that make sense?
It does, yes, thank you.
All right, Jeremy.
Thank you very much, Juliusz. In fact, my question is, I think, picking up on some themes of the previous questions. I was trying to think of a simple schema for describing the various aspects going on here, and it seemed to me that one could perhaps say this, and it'll involve a sort of contrast with the Bellot case.
Mm-hmm.
If you have a certain theory and it has a certain bunch of models and you think they're good for describing, explaining a bunch of phenomena, and you then are concerned with revision, perhaps to replace by a better theory or to mesh with an adjacent theory, as in the Bellot example, mesh with the adjacent quantum mechanics. There are two broad things you might expect you have to do. One is to adjust the set of models you countenance by contraction or by expansion. And the other thing you might do is, without throwing away solutions or adding solutions, without actually changing the set of models, you might think, I've got to reconceive the degrees of freedom in each model. And the Bellot example is the latter. You don't throw away any solutions of classical EM when you learn AB effect. But it is true that the literature from which you springboarded your discussion, physically reasonable spacetimes, it is cast almost entirely, I suspect, without having read it, but the way you spoke about it in my slight acquaintance, in terms of cutting down the set of models from the set of all possible Lorentzian manifolds, as your examples gave. I think that contrast may help navigate one's intuitions about the different case studies. In particular, I think you see that ADS-CFT, you said you can't really dismiss it as a toy model because it's a vast literature and it's so rich and fruitful. But you know, toy model suggested another silly word to me, and that is playground. ADS-CFT is the playground into which hundreds of people flooded because of the enormous attractiveness of finding something you can do where there's a lot of intellectual technology to explore and apply, right?
Right.
I would say that, you know, just to round out the question, the four big bad signs about ADS being not empirically useful, right? Oh, those 4 bullet points, it was so depressing list, you know, the sign of lambda down to the nonlinear stability issue. That doesn't stop those guys, because guess what? They're not trying to cut down or extend the set of GR models to describe the cosmos. They don't expect ADS to describe the cosmos. They regard it as a theoretical playground for probing creatively what might be the best degrees of freedom to think about in combining the quantum with space-time. Sorry, long speech, but I was trying to round out the themes from some of the questions.
Yeah, good, thank you. That's very useful. I agree that there is in a way here, we're not adding or removing models. It's rather we shifting our attitudes about models that we already have in the light of other things that could be done with those models. So that's one important thing. The second important thing is, in a way, the bigger question in the background is, why should we care about the ADS-CFT duality? Yeah, I fully agree with you. It's a sort of promising playground, but it has nothing to do with or very little to do with the real world. And so, in a way, this sort of considerations that I drew here are perhaps a way of saying that it doesn't have that much to do with the real world.
Yes, well, as a cosmology, it might not. Sorry, quick follow-up, if I may, Martin. It might have nothing to do with the world as a cosmology, but it might afford one insights.
It may have quite a lot to do with near horizon of extremal black holes, or right. But then in that case, this is no longer a playground, because this is something that actually seems to represent something like near horizon geometry of extremal black holes or other things like that. And those considerations about what's a physically reasonable space-time model for representing a particular subsystem sort of come back and potentially bite us if we would like to claim that this is a good model for representing those systems.
Thank you.
All right, I think now it's Kareem in class. Peter had a question, but he had to go, unfortunately. So I guess he'll contact you directly. It's in the chat. So
oh, thanks. So it's my turn. Thanks, Juliusz. That was really fascinating. I only had a couple of one comment we've discussed before, but I thought I'd raise it again because I think you could frame it interestingly and a more like example. So I think like it's salient, I think, with the comparison of the Clark-Gouin plasma ADS-CFT that there are also analog models of white holes, of course, right? So the original fluid analog that Unruh did was of a white hole,
right.
And then probably even more excitingly, the fiber optic analog models, you actually have a white hole and a black hole in front of and behind the laser pulse. So I think that's one other function of white holes is basically to explore things like Hawking radiation via the analog models. So I think that's quite interesting. But the other thing, the main thing I was just going to push you on a bit about is one thing that you haven't talked about is the role of the observer in this. And so, like, it always seems to me that one way of thinking about white holes would be to have a black hole, but then have an observer with an opposite arrow of time. And so for that observer, our black holes would be white holes. So in that sense, there'd be so what's physically the question is then not whether the system is physically reasonable or not, or but it's whether the observer is physically reasonable or not. Is it physically reasonable to think of an observer with an opposite arrow of time from us, and we don't have to change anything about the structure of space-time?
Yeah, right, fair. And so in that case, if we have an observer with the reverse arrow of time, then some of the considerations, like when does it transition into normal matter, may not arise anymore. Yeah, white holes are. I think it would be great if we discussed the white holes in some more detail in the connection with the Brian's CPT book, perhaps at some point, because there is a sense in which some of the arguments for ruling white holes as unphysical, so like the instability arguments, seem to need something like the assumption that this is the direction of time and we picked it right, and only then the arguments can go through. And one could perhaps, in the context of questions such as the one you asked, could see those assumptions as to some extent question begging. But there are also at least 3 different classes of arguments for white hole instability, and some are not very convincing, and some are a bit better, and some I don't understand yet. So that may depend on, those issues may depend on the particular argument we're considering.
All right, let's move on to class.
All right, thanks, Juliusz, for your talk. It was thought-provoking, as people say. I have one comment and one question, but I'll try to keep it short. So the comment is, so normally in, say, the foundation of quantum mechanics, the Bohr strategy would be that the interpretation of quantum mechanics depends on its classical limit, namely classical physics. And now you seem to do the opposite, is that right? So you're saying the interpretation of classical GR depends on the quantum theory where it supposedly comes from.
Good. I don't want to say that this is necessarily what happens. I want to say that, but this is a very useful way of thinking about this. I agree. What I definitely want to say that sort of if one accepts the ADS-CFT or black to white hole quantum transitions, then one seems to, in a way, redefine what solutions are reasonable in classical limit. But I don't want to claim that this is what should be done. I think it's a case of, you know, we could say this is what actually happens, but whether this is a morally permissible thing to do is, I think, a step that I'm not necessarily willing to commit.
All right, yeah, so there is the danger of circularity, I think, that the quantum and classical theories depend on each other in some sort of a vicious loop. But this is, my real question is different. It's inspired by what I call Ehrman's principle, and it's sort of about the question to what extent physical reasonableness is an approximate notion. Namely, if you take ADS as one of your two main examples, then you could take a very small negative cosmological constant. And so you could maybe say the space is only very, very little non-globally hyperbolic. And where is the end? So what's the limiting case? I mean, is it strict? Either lambda is negative and hence the space is non-globally hyperbolic and hence not physically reasonable if we follow Penrose's strong cosmic censorship. Or is this a sort of a gliding scale with approximation in being physical, reasonable or not?
I would expect it to be the latter. I would expect it to be, because I don't think the conditions are sort of set in stone and dependent on the context, they vary. And so I would expect it to be more like a gliding scale.
But then the argument becomes much more complicated, I think.
In what way you have in mind?
Well, see, the relationship between the classical and the quantum theory is more subtle if you include gliding scale possibilities, I would say. I mean, it's already a limiting relationship. And if this is what I was aiming at in a way, and you seem to confirm this in prayer, if you add physical reasonableness being some sort of a limiting notion, which, so it's the opposite. So physically unreasonable may become physically reasonable in the limit where lambda goes to 0. I don't have any further analysis. Just an observation that it becomes very hard then to give examples from quantum theory that exclude something, because this notion of exclusion has become vague now.
Okay. I'll keep thinking about this. I don't have an obvious reply at the moment. Thank you.
Well, can I say a very small thing?
Yeah, of course.
At least in the cosmology model that I've worked on with Sean Gribb, it kind of behavior changes dramatically as lambda goes to 0. There's really 3 families of solution. There's like a negative lambda family, a positive lambda, and then the 0 family, and they all have qualitatively different behavior. So I think you might get some strange things happening with difference between negative and 0, at least in some models.
Any more questions? I had one, but I being host, I kind of put myself at the back of the queue. Eric, you still have a hand. Jeremy, you still have a hand. Is that just because?
No, I was putting myself at the back of the queue for another question.
Okay. Well, okay. So I had just a minor comment. Yeah, on Kareem's point, by the way, about Lambda, it's interesting. A nice way of seeing this from the PDE perspective is just basically anything that's local or semi-global. You can bet that Lambda might not have such a major role, but as soon as you have something global, then Lambda can really change the picture, and that's something you see in all kinds of ways, not just cosmology, but black hole formation, instability of Cauchy horizon, etc. So that's just a little follow-up, but more in line with just more directed towards Juliusz's talk. So in a way, right, the perspective from mathematics is to say, well, I don't know what's physically reasonable, but I'm just going to take a class of initial data and evolve it according to the field equations, say in vacuum or with some particular assumptions on a matter model. And then I'll see what I'll get. And if I obtain a particularly unfriendly or unwanted or undesirable feature, such as a Cauchy horizon or a naked singularity or whatever, then I will ask the question, well, was that because my data was poorly chosen? And is it the case that if I go to generic data, this disappears? So in a sense, the mathematicians of GR are not, the idea that we should take the set of possible, topologically and geometrically distinct spacetimes that you could consider. I'm thinking of cut and paste. I'm thinking of closed time-like curves. I'm thinking of whatever you want. Take that whole entire wonderful collection, which is very fun to think about, and just say which of the ones are good, which ones are bad. From the mathematical perspective, that question's irrelevant. Like that, you just take initial data that seems somehow interesting enough or reasonable enough to consider, and you see what the equations tell you, whether or not you expect certain features to occur generically. That's what the initial data crew would tell you. In particular, with regards to ADS CFT, there is a kind of feeling amongst mathematical relativists, the ones that perhaps care more about physically salient or physically reasonable things, that the whole thing is a playground and it's fun, but ADS being unstable and all kinds of issues to do with using a fixed background and doing all your calculations within that seem to them to be utterly missing the point of what's a physical system like. So from their point of view, ADS CFD is very interesting, and it generates a lot of literature. It might generate interesting mathematics, but it has very little bearing on what they consider to be a physically relevant system or black hole. So yeah, I mean, the mathematical perspective is just to say, I will let the theory tell me what physically reasonable means, rather than I will start cutting down across the collection of different topologies and metrics I can put on a manifold, and I will start making my own judgments about what's physically reasonable. So how do you square that circle? What's your take on that?
Well, my take on that would be that I sort of permitted myself to have this broad enough characterization of what makes a space-time reasonable, that what I called relational features, for lack of a better word, such as some features being stable or not, can also enter in there. And so I would say that the sort of interpretative attitude I described can perfectly well accumulate something like nonlinear stability or instability issues as a sort of condition that we further use to sort of chop down on the models that do not have these features.
I get that, but let me put it a different way. For me, like the main question is, right, for me, the main question is something like, whatever the initial data perspective gives you, are the undesirable features occurring at a scale which is one for which a theory of quantum gravity should become relevant. So for instance, suppose I am uncertain about whether or not the nature of a singularity inside a black hole, Schwarzschild black hole, is really a crushing one, or if there's other things that, going to come into play. If I'm probing the theory in a domain where I know I should no longer trust my field equations, and for whatever reason, and that's something we see in other contexts, then what is the picture that quantum gravity should tell me, and how should that picture be amended? If, however, my undesirable or unphysical features are coming in at a scale where I shouldn't expect anything quantum gravitational to be relevant, right? For instance, the Cauchy horizon in the Kerr black hole, you can imagine that it, for certain choices of the parameters, that can happen at a perfectly large scale, So in that sense, what's physically undesirable about closed time-like curves or etc. are happening at a scale where I shouldn't be thinking of quantum gravity as somehow becoming relevant. It's occurring at a different scale. So for me, what would be interesting would be delineating in all the situations and all the scenarios in which we think a theory of quantum gravity should change our picture of what's physically reasonable, delineating, understand that from the point of view of the scales involved and the phenomena involved. So what are your thoughts on this point?
Let me rephrase it to see if I broadly get the picture first. So you seem to be saying, from a sort of initial data set perspective, what I do have are initial data and the equations that I want to solve, and different sorts of things may arise in the solutions of those equations. And what you would like to have is a sort of condition that tells you whether you should be expecting some semi-classical or quantum corrections to the solutions that you have in particular cases, and the explicit characterization of those cases.
Yeah. So what turns out to be physically reasonable or unreasonable hinges on where the expected corrections should come in.
Yeah.
And so the features that are deemed unreasonable are subject to that scale.
And so if the scale is
for instance,
large enough, the connections are expected to wash out and not contribute much to the original classical solution that you have, and so on.
Yeah. So for instance, if the correction because of quantum gravity is something that occurs at a really small scale, then essentially I shouldn't broaden my class of what's physically reasonable if I'm probing GR away from that scale.
Yeah, sure.
Right. But that changes everything, right? That changes everything, because then where GR breaks down changes completely on the kind of breakdown we're talking about, right? Whether it's singularities, whether it's causal, whether it's whatever. So take the Kerr solution, right? The breakdown in the causal, etc., that happens at a perfectly fine scale, right? The breakdown of the blow up of certain curvature components in, say, the Schwarzschild solution will be at a different kind of correction to come forward. So I think that's how I see the physically reasonable, like the changing of the class of what's physically reasonable, changing
would
that
be
changes
associated with yeah. I mean, I see the usefulness of this perspective, of course, and I expect that people who sort of heavily invested in black to white hole transition models would be able to give you an explicit answer and say, look, we have a semi-classical evaporation process, and we know like what corrections it includes because we expect black hole to lose mass. And then they will say, you know, at sort of which point during the evaporation or at which point during the evaporation they expect their additional effects to come into play. And they should be able, and they, in some cases, they do give explicit arguments for those effects coming at play at particular moments. How good those justifications are is another issue, because in many cases it's surprisingly around the page time that the corrections are expected to occur. But there is a story about why the corrections should show up at the particular moment and at particular scale. And then if someone provides me with such a story, then I think the sort of broad story that I told could also be sort of told from a initial value perspective.
I mean, maybe you should look for examples where all of this is, coming into play, and then you can discuss those examples and really get your interpretive feelings and your ideas. Really apply it to those examples and see how they how they work out. I think that'd be really interesting. I'd love to read that.
Yeah, I agree. Thanks.
Thank you for a lovely talk. Eric and Kareem, you both have a hand. So Eric or Kareem, who wants to go first?
Yeah, so this is a follow-up to Jeremy, who unfortunately had to leave. But as always, listening to him allowed me to clarify and sharpen my own thought. It seems to me that there is a difference in how one treats and understands the formal apparatus in the three different cases: the AB case, the ADS-CFT case, and the black hole white hole case, that are interesting, that really are interestingly different, and I think may bear on exactly may bear on how we try to understand what it is that these cases are getting us to change our minds about in our interpretations of the theory. So in the AB case, we have a formal apparatus. The Maxwell equations formulated using A and B and the Lorentz-Force law and potentials. And we had thought that we could solve all problems, perhaps not as elegantly and efficiently as possible, but in principle, we could solve all problems using the Maxwell equations and the Lorentz-Force law formulated using E and B. It turned out we were wrong. We actually have to use the potential sometimes. That's very surprising. So it turns out that we really do have to change our attitude towards the existing formalism of the theory. That's I think a plausible story to tell about AB. With white hole, black hole, these surgically constructed spacetimes that these guys throw around really are just classical metrics. They're a little odd topologically, and you get them through kind of mutilation and sewing back together. But they are really classical Ford geometries, Lorentzian Ford geometries. We don't need to change the formal apparatus or our attitude towards it at all. We just have learned that these things that looked kind of pathological from our previous standpoint, we now recognize may have some interest and use in regimes that go beyond what we think of as the classical regime. But ADS-CFT case is again entirely different. We have to import entirely new formal apparatus into the theory. We have to import the apparatus of CFT on flat spacetime. We have to import like a non-gravitational theory into the context of GR in order to make sense of what's going on. So I'm not sure what exactly this observation tells us, but I think my very strong sense is it's relevant somehow. And now I want you to tell me how it's relevant.
Well, I guess you could say it's relevant because it's not just because just looking at the set of manifolds and say those are nice, those are not nice, that's kind of limiting and not enough. That may be what happens in the black-white hole case, but that's not what happens in the ADS-CFT case, because there's all this additional stuff that comes along with it and makes those sort of space-time seen in more light, rather than yet another new cut and paste solution. Or sorry, that yet another new cut and paste technique. I guess this is what this is how I would paraphrase what you were saying. And then I agree that in the there's a sense in which this is different from Bellot's case, because our attitude to the existing formalism is one that is sort of doesn't change throughout all of this. So yeah, thanks. That's actually super useful, because maybe those cases are less homologous than I have thought previously. Mm-hmm.
All right, Kareem.
Sorry, I don't want to take up too much time if people have to go. I just, when Martin was talking, I dredged from my memory something that Tierman says in his big quantum gravity book. And it seems to be exactly like, I'm not sure it's necessarily, it sounds like a different case, right? Which is the global hyperbolic requirement in loop quantum gravity. And the way he describes it is quite interesting, is that he says, we impose the restriction classically for reasonable spacetimes, because the whole framework requires it, because it's canonical. But then we lift it quantum mechanically. And so in loop quantum gravity, you can have non-global hyperbolic changes. And he says even topology changes, although I don't know if their formalism isn't fully worked out. So I'm not sure exactly what that means. But in any case, at least Tierman's line seems to be that we keep the restriction classically, we lift it quantum mechanically. And I just found this remark, which is quite interesting, is that he says that semi-classical states won't have these weird topology changes. And so in this case, it seems like the quantum theory relaxes the physical reasonable assumption from the classical theory, but it doesn't give us a reason to think that the classical spacetimes which we thought were unreasonable are now reasonable, because they're still not featuring in the theory. And the semi-classical states don't have the unreasonable property either. So that seems to be a different example where studying the quantum theory and the semi-classical theory allows for a class of quantum structures which don't have the same properties, but doesn't change your view about what's physically reasonable in the classical theory. Hopefully that makes sense.
In contrast, again, with the black to white hole case, because the sort of whole point about the white hole case is that the late stages of evaporation can be perfectly well described classically, and we just need those small interventions at the incision points.
So I think it's probably like, it'll depend on each case, how we understand semi-classical transition, how we understand what, and then we can start understanding what the quantum theory can tell us about the classical reasonableness or not.
Right. Yeah. I agree.
Cool.
I may email you about the particular page in that book.
Yeah, it's page, you can write it down if you want, page 40. I have it open.
Okay, cool. Thank you. Sweet. Thank you.
All right, everyone. Are there any final questions for you?
I have one final announcement, which has to do with something that happened in the chat early on. And that's because this is recorded. So David Malamet, I'm very sorry that people use the expression Malamet-Hogarth spacetimes, but they use it, and I can't do much about it. I'm terribly sorry.
Apparently Schrödinger would never call it the Schrödinger equation, ever.
All right, everyone. Well, Juliusz, thank you so much for a beautiful talk. It's always a pleasure listening to you.
Thank you all. It was a great and very helpful discussion.
We've had lots of lovely questions. Really been a pleasure this morning. So thank you, Jamie, for organizing the event, and we'll all see you very soon.
Take care.